My name is Andre Horvat, and today I would like to share a few thoughts on the quality assurance in computational fluid dynamics and in a broader simulation analysis process. The lecture with the title Verification and Quality Assurance in the Simulation Analysis Process was initially presented at the seminar Quality and Reliability of the CFD Simulations in Warwickshire in April 2014. The subject is organized in 5 sections. In the introduction, we will look at motivation to set up a quality assurance process for simulation analysis and to draw a clear distinction between the world of physical experimentation and testing and numerical simulations. Project and analysis objectives will be discussed in the next section. Quite some time will be dedicated to different components of input control, such as toolset, personnel, analysis, and quality control procedures, as well as project specifications and requirements. Next, we will review elements of analysis process quality assurance and define its key performance indicators. At the end, I will say a few words on the importance of clients' communication and summarize highlights of the presentation. It is worth starting the presentation with the following statement. Simulation analysis process is used increasingly in engineering world to complement experimental and testing programs or even to substitute them. The reasons for this are economic, as the simulation techniques offer greater flexibility in managing testing environment, faster turnaround time, more comprehensive post-processing options, and lower costs. In some cases, safety considerations make physical testing impractical altogether. Such cases can be found in fire engineering, nuclear safety, and space equipment design, to name just few. Therefore, an overall trend in engineering process can be recognized. Design by experiment or by test is being substituted with design by simulation. In the world of numerical simulations, most of the effort is focused on recreating reality in a digital environment. Once the created virtual reality is representative of the analyzed environment, capturing relevant data is often much simpler than during physical testing. Initially, reality of interest has to be described using mathematical formalism. The question then arises, how well the mathematical abstraction corresponds or confirms reality. Such mathematical model has to be translated into a computer model that allows computational execution and simulation of defined real-world scenarios. Verification activities are required to confirm that the computational implementation accurately represents the mathematical conceptual description. In addition, validation looks at the degree to which the computational model is an accurate representation of the real world from the perspective of the intended use of the model. These assessment activities shall be an integral part of the simulation quality assurance process. More on the subject will be said later. Although the simulation analysis approach offers much greater flexibility, it also allows much larger errors to be incorporated in the development process much faster. To avoid mistakes and to mitigate their impact, some of them will inevitably stay undetected, suitable quality assurance or QA processes need to be set up and implemented with full rigor. Such QA processes are well-established part of engineering design and manufacturing procedures, but they do not always extend to the engineering analysis, although the related requirements have been defined by ISO 9001, 10 CFR 50 Appendix B, 10 CFR 21, NQA 1, to name just a few. It is important to emphasize that through all phases of the project work, the analysis objectives must be clearly defined and then agreed between all stakeholders. Such definitions shall be qualitative and quantitative as much as possible. This is especially true for the analysis output, its content as well as its form. It is recommended that clear separation between the design process and the analysis objectives is established. The analysis objectives have to be propagated from the top to the bottom. Each analyst or engineer has to understand the objectives, that is, what has been sold to the client. On the right is a cartoon that too often illustrates my experience. Quality parameters, that is, modeling uncertainty, numerical errors, results variability, and sensitivity, shall be integral part of the analysis objectives. To have any control over quality of the analysis output, we need to first look at the input control process. This consists of toolset control, that is, knowledge base, hardware and software, personnel, which have to be of suitable degree level, skills and experience, analysis and quality control procedures, either for lamp parameter modeling, CFD or structure or finite element analysis, project specification and requirements. Although these may represent a starting point of any project, they are often incomplete and subject to changes as the project progresses. Most of these activities are generic and applicable to different projects. They are time-consuming and therefore have to be accomplished prior to startup of analysis tasks. Validation and verification of declared software capabilities is an integral part of the input QA control. It can and usually is shared with software vendors. Let's look a little bit closer in validation and verification. Benchmarks are well-documented cases with understood physics for which highly accurate predictions do exist. They are used to independently validate and verify the declared software capabilities. Validation is the process of determining the degree to which a model is an accurate representation of the real world from the perspective of the intended use of the model. For that reason, computational results are usually compared with experimental data, although analytical and alternative simulation results are also often used. Verification is the process of determining that a model implementation accurately represents the developer conceptual description of the model and the solution to the model. To detect and quantify errors associated, for example, with numerical diffusion and dispersion, the computational results are compared with analytical derivations or with benchmark solutions that were obtained with higher order methods. The CFD community started to look into validation and verification problems some time ago. First papers appear in 1970s. At present, the discipline is well defined. The methodology and the associated terminology have been accepted. A number of online resources hosted by ERCOFTAC, NASA, and the University of Manchester, for example, are available specifically for validation of software tools. They offer experimental databases, conferences, and periodic exercises. Nevertheless, the available pool of experimental data is strongly focused on turbulence modeling problems. Today, the modeling problems may include turbulence, multiphase flows, combustion, structural mechanics, electromagnetics, etc. As the modeling is becoming increasingly complex and coupled, the supporting experimental data and the theoretical investigations are simply missing. Commercial software vendors may assist in the validation and verification process, but they should not be its primary source. It is important to assure independence of the software validation and verification, and that means to perform in-house testing. Such tests inevitably also include the software user, that is, analysts, and not only software itself. Although much of these activities can be performed independently from day-to-day activities, a certain degree of modeling, analysis, prototyping will always be required on individual project basis. A recent EFDA-sponsored 3PT project examined readiness of available modeling software tools for coupled analysis in fusion technologies, taking into account pre-processing capabilities, simulation methods, fluid mechanics, heat transfer, multi-phase modeling, structural mechanics, multi-body mechanics, electromagnetics, neutronics, parallel processing, post-processing, and visualization. A number of benchmark cases have been defined covering some of the relevant analysis areas. In front of us is one of the documents with a description of a benchmark case for wall boiling flow. The document contains a simple sketch of the simulation domain layout with the case definition, fluid properties, initial and boundary conditions. At the end, experimental and theoretical results are presented in graphical and numerical forms that can be directly used for comparison with simulation results. Input control also includes a periodic review of available personnel, their skill sets and capabilities. These problems should not be underestimated. They are often related to frequent and significant software changes, which nowadays can occur on an annual basis, and frequent career changes, either internal or external. People move from position to position, and this needs to be taken into account. In most cases, a suitable analysis process has to be identified prior to the start of the project. This means that the commercial, design, and analysis teams need to work together in preparation of the analysis specifications. Key performance indicators need to be defined. They can be commercial, such as hourly rate, desired profit level, technical, such as model implementation, results accuracy, etc. Scientific, for example, we would like to develop a novel approach. And last but not least, the level of client satisfaction. The analysis process plan needs to be as simple as possible to allow for feedback as the work progresses. Below is a typical Gantt chart for a CFD analysis. As we can see, most of the tasks are consecutive. Nevertheless, long simulation times may allow for parallel preparation, execution, and post-processing of multiple cases. It is crucial that task ownership is established. This means that associated project interfaces need to be agreed between different project groups and then set up and respected. My personal preference are project task lists that can be set up in Excel or online and allow instant feedback from project participants. Quality control plan is required at least implicitly to control if, how, and to what extent the key performance indicators are met. On the level of technical implementation, analysis checklists can importantly contribute to clarity of the inspected categories and the related qualitative and quantitative parameters. In front of us is an example of such technical checklist for CFD analysis. It comprises of general section with the basic analysis information, CFD analysis section that controls analysis processes such as geometry creation, meshing, model selection, their validation and analysis results, then the reporting section, and at the end of different notes and recommendations. Quality control plan tracks all phases of the project execution. It helps in recording evolution of quality concerns and eventual resolution of the captured problems. It is important to emphasize that the quality control plan needs to be a living document. After completion, it is a good practice to perform a project performance review. It will help improving efficiency and quality, including accuracy, of the overall analysis process. Its findings have to be fed back to update the analysis processes and the corresponding quality plans. At the end, I would like to summarize key points of the presentation and to stress the importance of communication with the client. Principles of quality assurance process applied to engineering analysis do not only improve the quality of the output, that is, higher results accuracy, less variability, better repeatability, etc., but they also reduce commercial risks associated with the project complexity. Technical aspects of the quality control plan need to be communicated to the client, which can be either external or internal. It is important that the client understands the accuracy of the analysis results and possible impact of the input parameter variations. Overstating the accuracy of the analysis results may have serious consequences. The results uncertainty, or at least its estimate, has to be an integral part of project deliverables. Although available computational resources may allow a more detailed picture of physics, they should not become a substitute for analysis accuracy and to cover for results variability. I would like to thank you all for your attention. I hope you found the lecture interesting. For any specific question, please do not hesitate to contact me.